Welcome again to the XX Network webinar on our performance testing. What I'd like to uh, again make clear is something about the context of all this. And for starters, I want to again affirm what a thrill it is to be a part of the distributed, decentralized movement, which in my view will probably turn out to be one of the key social movements because it strikes at the core of a lot of key issues. And I think it's generally, zooming in a little bit, regarded that two of the central aspects of this distributed uh, information technology systems world are security and privacy. And I'd like to drill down a little bit on each one of those briefly because they really will put the work that you're about to see, which is I think, fantastic, into some important context, which would be a pity if it were lost. So I think that in electronic money and payment systems like in blockchain, we are seeing the two biggest powers globally moving aggressively into this area. And what one can easily anticipate is a kind of militarization, if not weaponization or even sort of almost nuclearization of this space going forward, because it's a very key aspect of global power. And so I think we may see in the blockchain space nation states perhaps going up against what might turn out to be competing networks. And so we really have to amp up our game to be able to address things like quantum computers, perhaps in the future, but at the very least, we should try to find ways to use the strongest available cryptography, which is cryptography based on random functions, very large hash functions. We've seen over and over again that the cryptographic standards that governments have promulgated and are widely used in our community have been corrupted and subverted by governments. This is in the media. Not all of them, but some of them. So why would you think that the others aren't also corrupt? Why would a government promulgate something they couldn't break? I don't know. So that's one aspect. We really need a new level of cryptographic security in our space. And the other thing is, in the privacy sphere, I think it's become abundantly clear, if you've watched the Social Dilemma video on Netflix or been paying attention to the media over the last few years, you see that one of the biggest problems of our time has really been the damage done by manipulation of social media based on extracting traffic data and metadata, so-called. And so what we need is a way to prevent metadata from being collected, accumulated, made available. And so what we need is metadata shredding, as you have heard me say before. We have to sort of nip it in the bud, destroy it as it potentially could be created at each point, so it's never put together in any way that could be dangerous. So those are the two key things that I think are needed in order to move to the centralized vision we all share. And what we're going to see today is that the XX Network team has now successfully implemented the white papers that we put forward, I should say, just about a year ago. And all of the sort of claims and structure that was proposed there has now been proven true by these demonstrations and the running systems which are out there. But let me just tie this out to the impact that we can expect before we cut over to look at the technology itself. So by having a blockchain that can be truly privacy protecting and secure, we provide a really ideal platform for dApps. And one of the most critical dApps, if you want to think of it as a dApp, is voting for governance. And of course, we've seen a lot about that lately, but there's really in the cryptographic voting world complete disarray and disillusionment with the decades of proposals that have been around, because no one has a solution to the vote buying problem, the vote selling, the improper influence coercion online problem. And we here at XX Network have taken it upon ourselves to find a solution, and we put together a all-star team of scientists from around the world, academics, and we've got it written up, and it's partly implemented and in a couple different versions, and we're moving forward on that. It's called Vote XX. So it is a way to have a totally decentralized election that includes strong resistance to vote selling, vote buying, and coercion of voters. And it's unique in that, and that's an important ingredient for governance in decentralized systems, as you all know. So that is an example of a dApp that is enabled uniquely by this privacy protecting network that we've developed because of the metadata shredding, which is one of the aspects. And there's another. Let me give you just one other example, but you'll see these online. We've got a half a dozen really interesting dApps that I think uniquely can really work because of what we can provide. So we have one that is aimed at countering fake news, and it does this in a robust and interesting, engaging way to really involve, sort of crowdsource and create an incentivized environment for people to work on and engage in this area. And so that's also, the privacy is critical in a setting like that. And so, we have to resist tampering by nation states and like. So that's another example dApp. So now let me focus on what we're going to be seeing here today. It is, I think that the level of technology that we've said we could achieve, and now we're essentially proving we can achieve, is unprecedented in our space. Now, if you look carefully at the literature and the other systems that are out there, I've not found this level of transparency of performance or these levels of performance. I may be wrong, and I hope I'm wrong, but I think what we'll be showing is quite remarkable. So these are, I would say, crippled or in some sense limited, attenuated systems. In my view, perhaps only a tenth of the power that really could be available to them if they had, server class network connectivity or server class processors. So we've intentionally limited things, gone to some length to simulate a real deployment globally that it matches what we have today. Thanks to the community, we have like 250 nodes that are, people have built their own computers largely and are running our the messaging portion of our software globally, and this is a fantastic thing, and it's it's hard to say how wonderful I think that is, but there's another aspect which has been in stealth until like a week ago, which is the consensus and payments portion, which is using just these really beefy one-way functions. And so now we're showing that working, and moreover, so I have to, just once again point out that these were both designed together by our team, but then we broke up into two parts to build each part separately, and one came on stream before the other, but now we've done the difficult work of integrating them, and we're showing them working in an integrated or partially integrated fashion, but they're running on the same machines, and we're demonstrating the scalability from a couple hundred nodes up to like 1,000 nodes. And what you'll see is just, the linearities in scalability that you'll see are kind of the holy grail of distributed systems technically over the last 30, 40 years. And I'm not sure anyone else has really achieved them, but it's super exciting to see that. So in short, what you're going to be seeing is an unprecedentedly transparent reveal of the underlying details of the integrated system that demonstrate this, the performance and the scalability that we said we could get now for the integrated system, and in the context of it being uniquely able to provide these special properties, which is itself a tremendous achievement. So I just wanted to give that little bit of context, and now briefly I just introduce you to just a few of the fabulous people that have been working on building this over the last year. So I've already, I'd like to introduce the team, and I think you'll be able to see them here. So we have Ben Wenger, as many of you know, has been leading the Elixir portion of the messaging, and Will Carter has put together the consensus and payments team, and I think will be joined by Baltazar and Bernie, who have been doing a lot of the key development on that, and it's a unique opportunity to see all this great work in real detail, and you can send in your questions and people will answer them. So great. Thanks again for all of your support, and we're looking forward to working with the community on it and taking this where it needs to go.
All right, thank you, David. So I'm going to MC this kind of like the last webinar, and what we're going to do, if you missed the last webinar, is go over some of the results that we gathered during the 4-hour-long live stream of our scalability test. So we're going to kind of retouch on what that test looked like, how we set it up, what we were trying to demonstrate. We'll go over some of the results that we gathered, point out some of the irregularities we encountered, and then we're going to go into the next test, which is, it's actually been running already, but is our stability test, which is to show the network kind of being stable and running consistently on shared hardware for long periods of time. And so I think how we're going to do this is myself, Bernie, and Baltazar will kind of go through that scalability test. Feel free to answer questions during the webinar. We'll answer any technical questions that are asked. Any other questions, feel free to ask, but we probably, we may not have the right people with us to really give you, a quick answer. So we'll note them and then try to get you answers via Telegram or something. And then we also, I think, have Keith, who's on standby. Keith's been running our Node Lab in Seoul, Korea. He's been very, very helpful to really making these tests happen, and also throughout the development process. And also, I think, helping kind of be an interface between our team and our community of nodes. So he will be on call if people have questions about, I think, the node process. So we can bring him in if needed. So we're going to go ahead and get started with the presentation now. All right, so the first thing we want to do is note that there's two tests that we're going to show live today. The first is the performance test. This is going to be giving you a sense for how fast we can push the network on shared hardware. So the test that we're going to analyze that we did last Wednesday was just the consensus by itself. This will be a performance test of the consensus and Elixir on shared hardware. You can see the peak performance of this right now live on xxnet.io on that dashboard, and then the overall performance of this network in general will be on testnet.xx.network. And you can kind of see what the average has been over the period of time that it's been live. We'll bring these dashboards up later as we go as well. So first, let's take a recap and look at what it is we were trying to demonstrate during these tests. So we have three separate goals or main goals that we wanted to demonstrate. The first that we demonstrated last Wednesday was scalability. So we wanted to demonstrate that as this network grows in size, as the number of networks increase, the performance of the network remains consistent, and you know, we still get the same throughputs, we still get reasonable finalities. The second thing we wanted to demonstrate that as that network grows, the network resources that are required to support that performance grow linearly with it. So this highlights one of our key technological advantages or properties, which is endorser sampling. You know, normally in these networks, if you need to send data out to every node in the network, you start running into quadratic or even higher network resource requirements, and that really just limits the scale or the size to which your network can grow. So what we wanted to show here is that we could actually, you know, grow the network and the resources would scale proportionally. And I think you're going to be excited with what we show here today. And just to recap, that test was run on December 9th. It was about a 4-hour long live stream. We will make that live stream available so you can kind of like watch along on the dashboard with us as we push the various network sizes and transaction throughputs, so you can kind of see it for yourself. And then this is going to be like our analysis of what those results were. The speed test, as I mentioned, is really to push the joint integration network as fast as it can go in a live demonstration. Where you can go see that right now. We'll pull it up on the dashboard and talk about it a bit at the end. And feel free to ask questions. Just keep in mind that we are running on, you know, slightly less the test is being run on slightly less performant hardware than you'll see in our actual beta net. So take all these tests with a grain of salt. We'll go over what the hardware differences actually look like momentarily. And the stability test, again, was to demonstrate that Elixir and Praxis, the separate binaries or software packages, can both run together on the same hardware for extended durations, that there's no you know, major resource contentions that would make the network too unstable. So with that being said, let's take a look at what we saw with the scalability test. And you'll see here, this is a snapshot of the dashboard at one point during the test. This is when we had increased the network size to about 1,000, which you can see in the network parameters. And we were seeing in the last 10 committed blocks at this point, the peak TPS of 3,340 TPS with a finality of 2.5 seconds. So this was very impressive. So let's take a look at how this test was run. You know, we started with a network of 200 nodes, and we wanted to show it growing up to 1,000 nodes. We did this in increments of 200 nodes. So we did 200 nodes, 400 nodes, 600 nodes, 800 nodes, and then 1,000 nodes. At each point during this test, so for 200 nodes, for example, we would push varying levels of input transactions a second to see if the network could handle it. So we started with 500 TPS, 1,000, 1,500, 2,000, up to 3,000. So 500 TPS increments from 500 to 3,000 TPS. So we were trying to show that the network could handle those increments and get a sense for what type of resources it was using at each of those data points. During this test, if you remember, or if you've watched our previous webinars on our consensus, you'll know about endorser sampling. During each block, we only use a relatively smaller subset of the network to receive and process the transactions, and this is what gives us our scalability properties. So during this test, we kept that constant through all the network sizes, just to make the data points a little bit clearer to analyze. And we chose 200 endorsers. And so it's important to note that for the smallest network size, which was 200 nodes, because the endorser set size was 200, every node in the network was an endorser for every block. Subsequently, for the 400 node network, with an endorser set size of 200, every block, about half of the nodes were endorsers for each block. And then, moving on to 1,000 nodes, basically for every block, a fifth of the nodes in the network were an endorser for every block. So that kind of gives you like a mental image of how this is happening. And then we did basic or standard BFT assumptions during this test, where we assume that 2/3 plus 1, or roughly 67% of the nodes in the network, are honest. And the quorum percentage, basically the number of nodes in that endorser set that are required to approve a block, is roughly 56%. And then this is just to recap on the differences between the hardware that was used in these tests and the hardware that we currently have available for our BetaNet nodes. So for the test that we ran for the scalability test, we were using AWS C5.4x large instances. These are 16-core single-threaded instances. They have, we were roughly using 200 gigabytes of GP2 storage, and 32 gigabytes of RAM. So comparing this to our BetaNet hardware nodes, each BetaNet node has, just to go back to the AWS nodes, we're actually running 2 nodes on each of these instances, so they're sharing all these resources. The BetaNet nodes themselves have 8 cores double-threaded, 1 terabyte SSD, about 16 gigabytes of RAM. They also have an NVIDIA Turing GPU. And we've set the recommendation or the requirement for BetaNet nodes to be about 100 megabits per second up and down. So to give you a summary of how these compare, because the 2 nodes in a single instance are sharing the resources, each instance is really only getting about 8 single-threaded cores compared to the 8 double-threaded cores in our BetaNet. Similarly, they're sharing storage and RAM resources. I think the GP2 storage that we're using in AWS is over 10 times slower than what you would get in a standard SSD. So again, we're going to see much better performance in a lot of these tests once we move towards launching this on BetaNet hardware. The bandwidth is limited. Well, when we first introduced this test, we had limited the bandwidth to 100 megabits per second up and down using Linux traffic control, and we inserted some artificial delays of 150 milliseconds round trip time. If you watch the live strip, you'll know that we were delayed because we were running into some issues with this. So we actually had to deactivate these limitations. So the approach we took, instead of creating a hard limitation on bandwidth and creating hard delays, was to remove that limitation and instead track and record what the bandwidth and network resource usage would be, so we could just report it back to you. So in summary, the hardware that was used for these tests is roughly about half the processing power of a BetaNet node. The storage is much, much slower, and we don't have a GPU. Now, our consensus isn't using the GPU at the moment, but eventually we would like to optimize some of the transaction processing to use GPU, so that should speed some stuff up as well. So now we're going to get to the actual results. I'm going to let Bernie and Baltazar kind of give you a rundown on the results that we saw and what they mean.
Thank you, Will. Hello, everyone. So the first graph we want to show you is finality versus network size. So as you can see, mostly finality is remaining near constant as the network size increases. So you can see we're increasing from 200 to 1,000 nodes. And let's take a look at like the lowest TPS 500. You can see it remains pretty stable under 1 second. Then once you increase the TPS input, so transactions per second are coming into the network, obviously finality will increase. But when you move to more nodes, you actually see, for example, in 3K TPS, you see the network performing better with more nodes than with less. And this is just because of the way endorser sampling works, and we'll explain more about this later. So I'll just like to point out, like, the data points for the 600 node network are looking a bit higher than expected, and we will provide a potential explanation for that later as well. So next slide, please. Okay, so this is basically the same data points, but now shown in finality versus TPS. And as expected, finality just increases linearly with the TPS. So this is expected. The more transactions you need to process, the longer it takes to process, to like validate a block and to actually do the state updates. So that's expected, but it's important to see that with for all of the different sizes of the networks, all the numbers kind of match up quite evenly. So that's very interesting. And just we need to mention here that the 200 and 400 nodes networks actually couldn't cope with 3000 TPS. So if you see at the end of the graph, they're doing about 3.5, 3.6 seconds finality. And as we explain later, we have a maximum batch of transactions that can be included in a block. And this was set as 10,000. So if you divide 10,000 by 3.5, you can't get 3000 TPS. You will need the finality to be 3.3 seconds or under, which is achieved in the other network sizes. Next. And here we can see the bandwidth usage. So basically bandwidth usage is decreasing as the network size is increasing, and then it starts increasing. So this is basically an artifact of endorser sampling. So endorsers are actually gossiping the full transactions to each other, and this is about 5 times more data than any other node is gossiping, because most of the transaction size is the quantum secure signature, about 80% of this size. And every node that is not an endorser is not going to check that signature, so they don't need it. So they just gossip the transaction data, which basically means, oh, I'm sending this much money from here to here, or this coin here to here. And this means that, for example, in 200 nodes, everyone is always an endorser. So you can see the bandwidth is quite high, especially for higher TPS. So it goes very quickly above the BetaNet bandwidth restriction of 100 megabits per second. But then, sorry, go back please. So as we increase the network size, the amount of time you're an endorser is decreasing. So when you go down to 400 nodes, you're only endorser 50% of the time. And this means that, yeah, while we're increasing the network size, you can see the bandwidth actually decreasing. But then at the end, it starts increasing again. And this is just of the effect of the other side now, other side of the coin. The more nodes you add that are not endorsers, they're gossiping less data, but there are way more nodes than the endorsers. So that bandwidth will start creeping up. So we see that like this kind of reversed bell-shaped curve or something. Yeah. So next slide.
Just point out that like the space between the lines, as you can see, when you increase the number of transactions, it's actually pretty similar. So you can see that increasing by the same amounts, the same steps of transactions, you can see that they are most like linear, that step as well.
Yeah. Yeah, that's what we're showing here in the next slide. So the bandwidth usage is kind of increasing sublinearly with TPS, but the here in this slide is very clear that the 200 node network cannot cope with higher peak TPS. So after 1500 TPS, it's already using more than 100 megabits, like clear over the line. For the 400 nodes as well, it starts about 2200 TPS, and then you can see that it tops off the bandwidth. So it actually doesn't reach the 3K TPS because of what I mentioned before about the maximum batch size, which we will explain later. But important to see here is, yeah, like we said, the bandwidth. You can clearly see that the 200 nodes, since they're always endorsers, they're always gossiping more data. So you can see for the 500 TPS, 1000 for basically every data point, they're using more. Then for 400, it's already lower, and once you start hitting really high TPS, it's above the limit. For 600 is actually like kind of a sweet spot, but these could also be affected by the higher than expected finality. So maybe something was not correct there, so that's why bandwidth is lower. But it could also be just, it's a sweet spot, like 33% of the time you're an endorser. You have 200 endorsers, 400 non-endorsers, and the bandwidth usage just increases quite well. And then in 800, 1000 nodes, you can see like higher bandwidth than 600, but still lower than 200 nodes, and just increasing kind of linearly.
So here we can see that we had some issues with traffic control, but I think was like we removed the limitations of bandwidth and latency, because we wanted to keep track of how much bandwidth we would be necessary and which limitations we would have besides bandwidth, knowing in advance that bandwidth would be the first limitation. So this helps us like checking the burst of like bandwidth usage in each node as well as we increase the number of TPS. Besides that, like we reached like some problems with the 600 nodes, not problems, but as Bernie mentioned, the results are a bit different, but this might mean that with 15-minute test is very short and so more susceptible to be affected by traffic variations between cloud regions as well. As Bernie mentioned as well, we have a batch size of 10K per block, so we are restricted with 200 and 400 node network. We can't reach 3000 TPS since half or the total number of nodes in the network are endorsers.
Yeah, so I just want to point out something about that. What we could do here to reach the higher TPS, and if you watch the live stream, you probably remember that in the 1000 node network, we raised the batch size to push up to 4K TPS. So what we can do here is like increase the batch size, but then the CPU usage would be the bottleneck. If you have unrestricted bandwidth, of course, the CPU usage will hit like around, I think we tried a batch of 20,000 and it was already not working. And this is because also of the round timeout. So we have a round timeout of 10 seconds. So if in 10 seconds the round is not finalized, you will have what we call an empty block, which is just a block without transactions. So basically the peak TPS you can achieve is always a function of the batch size and this round timeout, assuming unrestricted bandwidth, of course.
So as you can see here, we have, if we change the consensus settings, like basically increasing the batch size or increasing the block timeout, we after see hardware like restrictions in the resources. So it's about the balance here that we need to analyze as well as we're doing here. So basically these results show that we scale linearly, and it's worth mentioning that these tests confirm the benefits of having an endorser sample, as previously mentioned. So 200 endorser network size, it's performing worse than 1,000 in terms of scalability, because in terms of results at TPS, because it can't reach that much because all the network is an endorser. Besides that, we actually reached 3,000 TPS even though it was without bandwidth restriction. So this is good to point out that these numbers are worth mentioning for test purposes as well, and we are gonna use this data to figure out how we can improve both consensus and how we deal with these consensus settings and hardware restrictions as well.
Thank you, guys. So with that, I think we're going to move over to the stability test. Again, if you have questions about what we were talking about the test itself, feel free to put them in the YouTube chat or our Discord. I think we have someone monitoring Discord, and we'll try to answer them at the end of the presentation. So now we're going to look at the stability test, and Ben's going to walk us through what that looks like now. I believe it's been running for a few days. Is that correct, Ben?
Yes, it is correct.
All right, so why don't you walk us through the
so
setup?
So the specs changed, and we'll talk about the issues that we ran into. But the goal of this test was twofold. In part, we wanted to show that the CMIX and consensus can run together, and the hardest part about that is resource sharing. And we put a lot of effort into that. A large part of that is offloading CMIX on the GPU, which is also necessary to make it run in consumer available hardware. And part of it is just the proper speccing of the network, making sure that the number of that the amount of bandwidth available is correct, that the hardware available is correct. And so we initially plan on having 9 database nodes and 10 nodes in our node lab running CMIX. Unfortunately, ran into some bandwidth limitations. We reduced those number of nodes to the minimum, which is 3. It's still a valid test. But the as you'll see, the specs show that the two interoperated well. There's not much to say other than that until I show the data. But basically, what we ended up having was our goal is to maintain 1,000 TPS. As you can see from this graph, we've hit it for the majority of the time. We've had some issues. We had a short outage on about 12 hours after launch, and then yesterday we were doing some testing. We reduced the TPS to try to see if we could fix some issues, which we'll talk about as well. But we could have run 1,000 TPS during that entire time, but we were trying to see if we could solve some problems, which I'll talk about. So we can go to the next slide. So here's the resource usage on the node, which is running both simultaneously, or one of them. So first you can see that none of these numbers seem particularly large. So the CPU usage doesn't seem to exceed 10%. Memory usage is high. We'll talk about that on the practice side. There are some memory leaks we found and we'll fix. And then the bandwidth utilization doesn't exceed about 20 megabits. And you can see that bump is actually because the snapshot was taken. We're running 250 TPS and then went to 1,000 TPS. And I'll talk about all of these. So the the obvious solution here is, wait a minute, aren't you over-specced? You're not using even the majority of your CPU or your bandwidth. And these numbers don't really dive into what's going on, which is that both consensus and Elixir CMIX are not these full-bore protocols. We get our performance by chunking up work in both cases and having them worked on my small subsets, which means that while working, you might use a lot of CPU or a lot of network, but your average utilization is low. The numbers that really show that the network worked well is the fact that we can see from the total utilization numbers that they're that they don't suffer performance issues. But on average, utilization is low, and this has confused many node operators, and it's not an obvious property. In general, it's one you try to avoid. But it turns out in this case that our scalability comes from, it's intimately tied to the fact that we don't have full utilization. So go to the next slide. We've got a few more resource usage graphs. So you can see that disk usage is fairly high. And this explains these specs in the BetaNet, in that Praxis, because we use these quantum secure transactions, they're quite large and a lot of disk space is used. Obviously, we'll continue to work to optimize this, but these numbers show that within reason we are functional for the selected BetaNet hardware. So, it's a trade-off that's required for quantum security, but it's within reason, at least we believe from this data.
Yeah, just to pitch in, it's quantum security definitely increases our transaction size, but another explanation between this disk usage is that we're simply just pushing an insane amount of transactions through the system, and those transactions update the state, which is stored on disk every time. So when you're looking at a network like Ethereum and they're only updating a state 10, 20 times a second, or handling the state of 10 to 20 transactions a second, you can understand why our disk usage at 1,000 or more transactions a second might be quite a bit higher.
So we went through a series of issues, which result in us lowering the number of nodes running both pieces of software. And basically, there's two coupled problems, which is that Node Lab, which is in South Korea, it turns out that its internet access is heavily shaped by, because it's a residential access that it has, it's it was using the amount of available bandwidth got reduced, and we also found out yesterday that we also ran some issues with data caps. So we reduced the number of joint nodes. We can avoid this in the future by deploying joint nodes to cloud instances with GPU, or spread hardware nodes across multiple locations. I expect we'll do tests like this in the future, and I'm sure that we will approach that differently. Ultimately, we were able to get the data that we needed and confirm what the properties that we suspected. We also had a deployment fault, which caused the joint nodes to go offline at around 4 a.m. We had to reconfigure them. It was a deployment mistake. These things happen. These tests are complex. We ended up deploying this test, I think, at least a dozen times over the past few weeks for various configurations to fix various problems. So, mistakes happen. Next slide. I'm going to hopefully some people from Praxis can tag in here, but basically the Praxis binaries have been now run for 60-something hours, which is longer than they had previously, and some slower memory leaks have been found. The first one is that when in sync mode, they're still kind of running some consensus stuff, which ends up using too much RAM. And it looks like there's a memory leak, which takes about 2 days. So yesterday we had a bunch of nodes go down, which we're able to manually reset due to a down memory issue, and they were able to keep going. So both of these issues I expect that we'll fix relatively soon. I don't know if anyone from the Praxis team.
I can comment on some stuff. So this memory leak took out 3 nodes, I believe. Yeah, it says there. We still don't know if it was like a memory leak that happens in all the nodes, because every other node seemed to be okay today. We checked on the RAM and it was under 4 gigabytes. So it might have been something like some different conditions that triggered an issue. And then we have the problem with sync mode. So whenever you start to fall behind with the network, you change to sync mode. And however, you're still storing consensus information because we have a pipelined approach, and like the naive implementation of just stored information, you're gonna need it. But this means that obviously the node will always run out of RAM before it ever catches up if it's too far behind. So this means that these 3 nodes that went offline basically cannot catch up anymore now with the network unless we push a fix to them, which we are planning to do.
So as an engineer, I see these as kind of the point of these tests. You learn things you wouldn't have learned otherwise. And in some ways, I find this encouraging because it's a little bit of a litmus test that this was worth it from an engineering perspective.
Yeah, because before this, we had run it for mostly, I think, 30 hours, the longest we've run our side. So this is definitely the longest it's ever run.
So want to talk about the next steps for integration. Obviously, we're going to patch the bugs that we found, have tests that show these issues as fixed. Elixir needs to anonymize transactions, and we're well on our way to doing that. We built this interconnect, which we discussed in the last webinar, and I expect that will come fairly soon. There is more investigation to be done on how these interact, because in theory, it is possible for Elixir and Praxis to need to use bandwidth at the exact same time and for them to cause problems. We've not seen any evidence of that being significant, but that doesn't mean it doesn't exist. It just means that there's a misstep in recovery, which says good for our software, but in our design approach, but doesn't mean the problem doesn't exist. So we need to go in and probably get bandwidth utilization and timings down to millisecond levels, and really see if over a long period of time we ever have any of these misses, and then develop strategies for dealing with them. And often you can't, because Elixir and Praxis are two fundamentally asynchronous systems which connect. So the real solution isn't to really solve the problem, because synchronizing them would be quite difficult, but it's to decide a priority of when you have a miss, which one misses, because you can either have both of them slow down or you can slow down one in favor of the other. So figuring that out is going to be an interesting engineering challenge.
Just to point out here that one of the reasons, since we remove the bandwidth restrictions, is also to see how both Consensus and Elixir sometimes use an insane amount of bandwidth, but for short periods of time. So as an endorser, for example, since you are just a percentage of the network is an endorser, when you receive more information, you're using more bandwidth. So just for specific periods of time, you use a lot of bandwidth, but the average goes down because it's not just short periods of time. So it's good to see how much bandwidth in those cases you're using, more than 100 megabits, but even though the average is lower.
Right. And obviously, if nodes don't have more available, they won't be able to use more. So
exactly.
Fine-tuning that and figuring out exactly what those limitations are and handling them intelligently will be important. We're eventually going to want to schedule Elixir onto the Praxis random. We've got some designs for this, and it's an interesting challenge. I don't know if something similar has been done before, but we'll figure it out like we've done everything else. It's in some ways this is also a software architecture problem, because right now we have the centralized server. Figuring out how to migrate without too much effort will be an interesting process. We also need to Praxis needs to add checkpoint blocks.
Yes.
Maybe someone of Praxis can explain that better.
Basically here, as mentioned before by Will, when talking about the disk usage, since we're stateful, we need to keep the state of the nodes. And when you reach multiple rounds, thousands of rounds, you're always storing a huge amount of state, since we have more transactions per second as well. And so we need to find a way with checkpoint blocks of compress this information and have blocks in more periods of time. For example, in our dashboard, you can see that right now we have 1024 blocks per checkpoint. So we compress those blocks to reduce the disk uses.
Also, I think this helps. point out some of the nodes on the dashboard when we get to it after this are down or in sync, and they're a bit behind the network. Checkpoints will help us allow these nodes who fall behind, say you go offline, your node goes offline for some time, like your internet dies, or you need to upgrade it, and it falls behind the network. Checkpoint blocks allow you a way to quickly catch up to the rest of the network efficiently.
So this can also be a benefit for bandwidth usage as well.
Yeah, and then finally, we want to prepare all of this for BetaNet release. So we want to do these same types of tests and demonstrations on BetaNet hardware, so the 264 nodes out there. So, this was another kind of side goal of all these demonstrations, was to catch any potential bugs, memory leaks, or issues, and really handle them now when it's easy for us to kind of dig in and figure out what's going on before we start deploying it to people's hardware. So hopefully this whole process will make the deployment to BetaNet a lot smoother.
Yeah, and I do want to point out that this isn't an ordered list. I don't specifically deploying to BetaNet is not dependent upon finishing all of these. I'm not sure exactly what that arrangement is, but
Right.
I don't want to scare anyone thinking that we've got a ton of work to do before we start deploying. Not to say there's nothing, but this isn't an exhaustive list where each thing has to be done in this order.
Okay, so before we get to questions, I actually want to take a look at our dashboard. So this is the dashboard that we're looking at for the overall stability test. And as you can see, this has processed roughly 181 million transactions since it started. We're pushing on average, so this is the TPS at the bottom here is the average number of transactions that have been processed since the network was started to now. We'll move over to more of like a peak value in just a moment, so you can get a sense for how fast we're pushing it now. And then we're looking at an average time to finality of about 1.64 seconds. You'll notice in Elixir we're pushing about 125 messaging transactions a second. This is lower than the 1,000 messaging transactions per second that we're pushing in BetaNet. And the obvious reason for this is we only have a single team that's constantly reprocessing batches. So they don't have the same capability as in BetaNet, where you have hundreds of teams that can start doing pre-computation simultaneously. Each one because we're only using 3 nodes to run a CMIX team here, they basically have to do all of pre-comp and all of real-time every single batch. So that's why we're running this lower than the BetaNet spec. So if we take a look now at the peak of what we're pushing through at the moment, you'll notice that we do have a handful of nodes offline. This, again, is just going to what was mentioned before. We don't have checkpoint blocks implemented yet, so when some of these nodes fall a little bit behind, they have connection issues or what have you, they don't have a chance the network's moving so fast that they actually can't catch up. So once we have checkpoint blocks, it'll be much easier for these nodes to catch up, and they won't fall permanently behind. So you'll see like that node fell back at around 89,000. Going further down.
We have two new nodes down there offline, so
Yeah.
we're going to investigate if it's the same memory issues.
Yeah, and these 3 at the bottom, you'll notice are our hardware nodes. So these are the Node Lab nodes that Keith is running in Korea. They're running on basically BetaNet spec hardware in his lab, and you'll notice that they're all up and running. But you can keep an eye on them. They're always at the bottom of the list. Again, these are the nodes that are running both CMIX, batch processing, and the consensus mechanism. So moving back up here to the performance metrics, someone correct me if I'm wrong. Are we pushing 2,500 TPS or 3,000?
2,500.
Okay,
Yeah.
so we're pushing 2,500 transactions a second here. You'll notice the TPS is roughly achieving that. We're getting a slightly longer finality than we saw in the last tests, and the endorser set size is slightly different than what we had set up. Also, before in the previous test, we had 200 nodes in the network. 200 nodes as endorsers for various network sizes. In this, we have 100 nodes in the network with the 30 node endorser sample size. And you'll see that it's handling 3,000 TPS, 25 to 3,000 TPS fairly well at 3 seconds on the integrated test network. So, what we would expect to see here is if the hardware nodes that are running both CMIX and consensus weren't capable of processing this TPS, we would expect them to fall behind during this test. So the fact that they're keeping up gives us a strong indication that they are capable of processing this throughput given the bandwidth restrictions that are in place there. And I think we're going to be leaving both these dashboards up for the remainder of the test, which is supposed to last a few more days. How many more days, Ben? 4 or 5?
Currently scheduled to run until Friday.
Okay.
We're less than a third of the way through, actually. Maybe a little more than a third. But
Yeah, and it's nice to see that, we've processed 181 million transactions here. I think Ethereum in general has processed only 1 billion transactions in the entire years or almost decade that it's been around.
Yeah.
So,
And Bitcoin has processed about 600 million, I think.
yeah.
So we will probably reach that. It's like
Very
an
likely.
unwritten goal, trying to reach the full Bitcoin network number of transactions in 1 week.
Right.
I want to talk a little bit about CMIX. You'll notice here that the MTPS, number of messages that this can process, is a lot lower than as is expected. This is because there's only a single team running. So unlike a blockchain, the mixed network increases its throughput performance as you add more nodes. So this is roughly on par. You can see that the average real-time duration is lower than the BetaNet network itself. We're actually trying to simulate here the effects of the network, and we're expecting, and especially from data analysis of the network itself, that we've got some nodes that aren't meeting various specs, and when dealing with them, we should be able to reach these similar numbers. Let's talk about a few other things. Lost my place, I apologize. This network, as they're interacting, is currently, I think it's actually not band limited. We had it before, we're having some trouble with the traffic control. But the tests we saw showed that it stayed under the acceptable limits, so we think that they will interact appropriately. And it's important to note that that these nodes, while in the same data center, in this, it is a data center, in the node lab, we're simulating 150 milliseconds of latency in communication. And if we take that out, for example, the real-time time drops under a second. So latency is a significant impact on Elixir CMIX speeds. So, that gives information to work on. The other thing is that this is actually not running the same version of CMIX that's on the BetaNet currently. This is testing the new version. If you go check the our Git, you can see that there's master, which is on the network, then there's release, which is what we're working to upcoming release. So this is actually testing the code which has support for clients and messengers, which we're actually gonna have another webinar on Wednesday. So including starting to release source code. So this code will hopefully go to the network in the very near future, and we're excited for it. the beginning of really utilization and being able to build things that send messages, releasing of the messenger. We've got more to announce on that front.
Yeah, so still a lot of exciting stuff to come. I think we're going to take this opportunity to start answering some questions. I'm going to get set up so that I can see my Discord so we can kind of monitor any questions that are coming from there. So I'm just going to put us on the splash screen, and I'll be back with everyone in about 3 to 5 minutes. All right, guys, we are back, and we're going to start with the questions. These are questions that were asked during the live stream of the last webinar. Some of these we've answered in some form during the presentation, but we just wanted to recap. Baltzar, you wanted to take the first one?
Yeah, sure. So basically in the last webinar, what we did was the scalability test. So basically we're just running consensus. So we can compare the finality with BetaNet, plus the scalability test, not the scalability test like we ran in the last webinar. The scalability that's currently running is running both software. So, but it's only having 100 messages MTPS, so messages per second, and not 1,000 like in BetaNet. And this can be explained easily because we're only using 3 nodes to run CMix. And when you have multiple teams, you can spread like that computation power and like that time that takes through different teams. So it's actually faster when you have more teams working at the same time. Plus, in terms of finality to the client side, you need to sum both the consensus finality plus the real-time finality in CMix. So that's actually the final finality for the consensus side, summing both finalities.
I think what's interesting here.
The latency. Sorry.
Oh no, go ahead. Go ahead.
Yeah, just the latency that you will actually see when you send a transaction will obviously be the CMix first, and then the consensus.
I think it's interesting to note here, one of the reasons why the scalability test didn't include Elixir and we just focused on consensus is because Elixir and consensus have very different scalability properties. Consensus traditionally gets slower as you decentralize the network or as you add more nodes. Elixir, on the other hand, actually improves in performance as you add nodes because you are able to have more teams running pre-computation in parallel, and you'll have more of those pre-computations on standby ready to be pushed into real time. So, showing scalability as the network increases for Elixir wasn't as interesting as for consensus, simply because this is like the worst case scenario consensus. Going to the next question, which again was from Alex. The 200 node test didn't reach 3,000 TPS. Was it expected? Yes, it was expected. We talked about this in a prior slide. Bernie, do you want to recap on this?
Yeah, so basically, because all the nodes are endorsers, everyone is processing all of the transactions. So what happens here is they're taking longer, so the finality is higher than the 3.3 seconds we will need with a maximum batch of 10,000. So since we're using 10,000 transactions per block, we would need the finality to be around 3.3 seconds, but it's actually 3.5 or 3.8. So what we could do to reach that 3K would be increase the batch size to 15,000, for example. And then if you do 15,000 divided by 5 seconds of finality, for example, you already reached the 3,000 TPS at the cost of an increased bandwidth, obviously.
Right.
But then once we increase the maximum batch even more, you will start seeing the round timeouts. So nodes don't have enough time to process, so they only have 10 seconds to process that many transactions. And this is actually a lot of transactions if you think about it, because like Ethereum blocks, for example, have 200, 300 transactions. We're talking about 15, 20,000. So you have the state free, like you need to keep the state, you need to make all of those updates, all of that takes insane amount of CPU and also disk.
Right. Another question that we've answered, but we'll just recap. Can I see the dashboard of this test? Yes, this is specifically for the scalability test, but also obviously the stability and performance test dashboards are live at the moment. The scalability test dashboard, that entire 4-hour long live stream, we will keep on YouTube, so you can go back and follow through it. If we have time, we might go through and like trim out some of the periods of inactivity where we were getting stuff set up, so it'll be a little bit more compact. So we'll have both available, just as time permits. And then the last question that we received during the last webinar was, why are you afraid of 1,000+ nodes if it is able to scale linearly? This one's actually pretty easy to answer. Obviously, yeah, we only tested 1,000 nodes. The reason we are afraid, and I was afraid, is because it's really expensive to push out 500. For this test at 1,000 nodes, it was 500 instances of AWS and run them for long periods of time. Like, these start costing thousands of dollars an hour. So that's why we didn't keep pushing it. Basically, for this entire test, the way that we did the deployment, we would deploy all the nodes that would be needed for the largest demonstration, and then we would gradually spin up nodes within those deployments. So, at 200 nodes, there are, 400 instances that were just sitting there. We're paying for them, but we're not actually using them. So you can imagine if we had pushed this up to 2,000 or 3,000 nodes, you're going to have, up to 1,000 nodes or instances just sitting there eating up money without really doing anything. Eventually, ideally we would love to show a test of 1,000+ nodes. So maybe we'll save that as a challenge for the future. So that's all the questions from the last webinar. Now we're going to start hosting some of the questions that are in the YouTube live stream. Maybe. So the first one, what are conservative TPS speed throughput metrics expected once the network is scaled out fully after release? This one is difficult to answer because obviously it depends on what scaled out fully ends up looking like. And I think it's actually linked to another question down here by Charles Perkins, which are, what are your hopes of the size of the mainnet at launch after 5 years? So maybe we should answer that question first and then go back to what that might look like for TPS speed throughput metrics. Ben, you want to take the mainnet size question?
Yeah, so I'm going to answer this in a roundabout way. I think that when talking about the size of the mainnet, obviously the real answer is as big as possible. 1,000, 10,000, 100,000, why not? But the real answer is that the size of the network should be analogous with its economics. And I think that the real kind of heart of our approach to this is not going to be setting a specific target goal, but trying to build systems which incentivize adding nodes as is appropriate for the throughput of the network. You can imagine that if you don't have much usage of a network and you say, great, we want a ton of nodes, what's end up happening is that the money to pay for those has to come from somewhere. And you end up having to kind of just inflate the value of the coin to meet them. So, you obviously need to start off with enough that the network has some chance of surviving. It's got enough security, it's got enough functionality. But what I think we're really hoping is that you've got an economically driven network where the number of nodes that are there is related to the utilization of the network, and as the network utilization goes up, it adds more, and that it's incentivized to do so. So to reframe this question, I really think that the independent variable is how much people use it, and that depends on us providing good software, which I hope you're going to start to see the beginning of that on Wednesday with our webinar on the XXDK. It's finding good utilizations, making good partnerships, finding and helping the community grow. So not going to give real numbers because it's really hard to imagine what they would be, and it's not immediately obvious what those scales are. But I really prefer to think in terms of the usage of the network and letting that drive it than just the pure numbers.
Yeah, and I think like just following up on your point about usage of the network kind of driving the definition of the network, I think it's important to just kind of link back to what David had mentioned when we started the presentation today, that we're also trying to build out interesting applications on our network, including the fact-checking application that he mentioned, the decentralized voting or secure digital voting, and then we have some other applications that we're working on in partnership with people. And so we're hoping that these do two things. One, these applications will bring users to the network, which will help us build out the network with more and more nodes and more capabilities. And then also that they demonstrate to developers the types of things that you can build on our network, so they can act as an inspiration or a demonstration on the types of actually useful projects that you can do with the XX network. So like with that in mind, assuming we do get some good pickup using the Messenger app, people sending transactions, all these partner applications, I would be comfortable saying that 1,000 TPS would be a very conservative metric for what we could achieve once the network is scaled out, and I would expect it to go actually quite a bit higher. So the next question is, individuals who want to be a mainnet node may not be able to get symmetric net cheap. So this basically means they have both 100 megabits down and up. This is something that's definitely the case in the United States, so I believe that this is true. And the question is there a way to support this kind of asymmetry? I think one thing that we've learned from this test is that it will in fact be difficult to support asymmetries that don't have at least 100 up and down once we start getting to significant scale, once we get significant throughput. So we're gonna think about this and find out ways to work around it. It might be the case that I'm not gonna say anything yet. We're gonna look into this and see if we can find a way to work with nodes that obviously can't get the symmetric up and down. I think at least initially, before the throughput starts picking up, they'll still be able to keep up with the network just fine. It's just a question of what happens, once the XX network becomes the most popular blockchain in the world.
I want to add something this, which connect back to my previous conversation, which is that there's a huge amount of value for the network in having nodes around the world and in countries, even where it's harder to run them. So my hope would be that we would figure out ways to modify the incentivization scheme to help incentivize to run in places where it's harder to run. I don't know what that would look like, and how you would do that in a decentralized network, decentralized governance is a very open question, and I don't have an answer for that. But those are the types of approaches that I think will lend well, which is that there's hard reality, there's hard ground truth, but part of the role of the network is going to be to make decisions on how to best manage that.
And then I think we're going to use this last question on here as our final question, and I think David wanted to take this, which is, are you guys going to have smart contract capability, a Turing complete language, and will this be possible for dApps? So David, are you still with us?
Hey, yeah. So it's been a great webinar and a lot of super excellent stuff we discussed. And it's been, I think we've done a great job of answering these questions. Let me just turn to this last question somewhat briefly and obliquely, and before thanking everyone and signing off, the term Turing complete is heard all the time in our community. And it has been used to, create some very big disappointments. And it's, I just wanted to remind people of what I think the origin of it is. I believe that Bitcoin deliberately decided not to allow branching because then you wouldn't be able to tell how long the smart contracts would take. And so Ethereum decided not to have that restriction. And so they made a big deal of saying that they were Turing complete, which, sounds very impressive. But let's step back and look at this smart contract thing for a moment. I think anyone who's really worked on this and thought about it realizes that these aren't very smart. In fact, they are just computations that everyone duplicates and checks. And so they inherently cannot have any secrets. There's no secret state. And so they cannot have their own keys. So they cannot make signatures, send encrypted messages, decrypt messages that are sent to them, protect private and personal data of users, and so on. So they're really not computers at all. They are replicated, transparent computations that have proven to be very, costly. I mean, as the network scales, every node is doing them. So we at XX have been thinking, trying to think deeply about this, and we've come up with a breakthrough that promises to provide what we hope will be super smart contracts, which will really deliver something useful and in keeping with the privacy aspects. And I think we'll find that this breakthrough is uniquely able to run on our network, and I think a lot of things will come together. These are early days, and I don't want to make any specific promises about it, but we are working with some major academics and companies, and there's a lot of interest in it. Still a little bit in stealth, but it looks quite promising. So that's about, all we could really say at this moment. Thanks for, being interested in this, and let us know if you'd like to, work on this or be involved in that sub-project. So having said all that, I just want to, I think it's very important to thank everyone in XX Network who's done the fabulous work that's brought us to this point. I think we've also done an excellent job of demonstrating very transparently where we are and how well this is all working. It's such a breath of fresh air compared to a lot of other things I've seen that have shown some what I think I've tried to argue are essential, critical components of the kind of world we're all trying to build here, and we've really got them working with your help. And so we're I think, speaking for everyone in the project, we're really looking forward to working with the community to move all this forward so that it can reach its potential.
Thank you. Thank you, David. Thank you, everyone, for attending. And just to remind everyone, we will be having another webinar coming up. I believe it's on Wednesday, and we'll be going over the XXDK and some of these applications you can build on top of it. So again, if you have questions, feel free to post them in Discord. And I think at the end of the next webinar, we'll again take some questions, and we'll try to answer any that have been posted since this webinar. All right, thank you, everyone, and have a great day.
Thank you, everyone.